Have you ever thought about whether we're truly alone in the universe or if there's more to our existence than what we see? What if the James Webb Telescope finally proves that we live inside a black hole? Join us as we learn more about this groundbreaking news that will make you question everything you thought you knew about the universe. So what exactly are black holes? They're like something out of a nightmare. Sure, you might have seen them in sci-fi movies, but the reality is even scarier. According to scientists, they're not just pitch-black holes in space. They're actually massive amounts of matter squeezed into an incredibly small area. Think of a star 10 times more massive than the Sun, all packed into a sphere the size of New York City. The gravitational pull is so intense that nothing, not even light, can escape from it. Scientists have been fascinated by black holes for centuries, ever since they pondered objects in space so massive and dense that they could trap light. The most famous ideas about black holes were predicted by Einstein's theory of general relativity. Essentially, when a massive star dies, it leaves behind a tiny dense core. If this core's mass is more than 3 times that of the Sun, gravity overwhelms everything else, leading to the formation of a black hole. Detecting black holes is no easy task since they don't emit any light. However, scientists have found ways to infer their presence by observing their effects on nearby matter. For example, if a black hole passes through a cloud of interstellar matter, it'll pull that matter towards it in a process called accretion. Additionally, when a normal star gets too close to a black hole, it can get torn apart, emitting X-rays as it does so. Black holes also have a significant impact on their surroundings. They can consume nearby stars, emit powerful gamma bursts, and even influence the growth of new stars in some areas while stalling it in others. But where do black holes come from? Picture this. Stars, once magnificent and blazing, meet their ultimate demise in a spectacular explosion called a supernova. From the remnants of these fallen giants, black holes emerge. Most black holes are born from massive stars that have reached their celestial retirement party in a supernova blast. Smaller stars, when they die, transform into something called neutron stars, which are super dense but not dense enough to trap light. However, if a star is about 3 times the mass of our Sun, it collapses under its own gravitational pull, forming a black hole. As these mighty stars collapse, something strange occurs near their surfaces. Time itself starts to play tricks. From the perspective of someone far away, time appears to slow down near the event horizon, the point of no return for anything falling into a black hole. It's like the star's clock ticks at a different pace compared to ours. Sometimes, when 2 smaller black holes collide, they combine to form an even bigger and scarier black hole. If a black hole teams up with a neutron star, they create a colossal nightmare that defies comprehension. Scientists have been grappling with the scale of these cosmic phenomena for years. Black holes come in 2 sizes, huge and small. There's a sinister mystery surrounding them that we can't seem to unravel. But here's the twist: small is relative when it comes to black holes. Stellar mass black holes, remnants of massive stars, can be as large as 10 to 24 times the size of the Sun. There could be as many as 10 million to a billion of them in the Milky Way alone. That's an astronomical number of black holes that could swallow anything in their path. But wait, there's more. Supermassive black holes are on the other end of the spectrum. They are millions, if not billions, of times larger than the Sun. They exist at the center of large galaxies, including our very own Milky Way. It's like a gaping dark void that's pulling everything towards it. Renowned physicist Stephen Hawking talked about black holes in his lifetime. His lectures were always insightful, but some of his theories couldn't be confirmed due to a lack of necessary equipment. However, there's hope on the horizon. A single scientific instrument is changing everything, and we're not ready for it. It goes by the name of the James Webb Space Telescope, also known as JWST, and it's here to plunge into the depths of our universe. Let me tell you, the JWST is no ordinary telescope. It's an engineering marvel, a testament to the potential of human ambition. Sure, we've launched other space telescopes before, and they've been doing their jobs just fine, but this one is in a class of its own. The JWST makes the Hubble, which has dutifully served us for years, look like a mere speck in the cosmos. The price tag of this astronomical wonder is a whopping $10 billion. Yes, you heard that right, that's enough zeros to make your head spin. And get this. It took the combined efforts of NASA, the European Space Agency, and the Canadian Space Agency to bring this marvel to life, not to mention the invaluable input from over 300 universities. But let's not forget the risks that come with such a grand undertaking. I know this isn't a venture for the faint of heart. The JWST is venturing into uncharted territory, pushing the boundaries of what we know and taking us to places we've only dreamed of. Following a successful launch, NASA recently announced that the telescope has enough fuel to last more than twice its minimum mission life expectancy of 10 years. Since its launch, the JWST has made many incredible achievements. It traveled over 1 million miles to reach its orbit around the Sun, where it will reside permanently. During its journey, the telescope successfully unfolded its massive 5-layer sunshield and giant main mirror, both of which had to be folded to fit onto the launch vehicle. Now, after NASA has fine-tuned and calibrated it, the telescope is almost ready to go into full operation. One of the most exciting things about the James Webb Space Telescope was when NASA announced that it had captured its first images of starlight. The first image taken by the telescope was of a star called HD 8446, resulting in a mosaic of 18 scattered bright dots from the star's light captured by the 18 mirror segments located on the primary mirror. NASA later released a new and improved image of HD 8446, in which 18 unfocused copies of the star were brought together in a deliberate hexagonal formation. Once the observatory successfully aligns the individual segments of the primary mirror, it will begin the image stacking process. This will bring 18 images on top of each other into one clear view. Thanks to its sophisticated technology, the JWST will help scientists investigate the early stages of the universe after the Big Bang. It will study what happened after the first stars formed, a period known as the epoch of reionization. This era refers to when neutral hydrogen was reionized or made to have an electric charge again by radiation from these first stars. This involves looking back billions of years, which is only possible with a powerful telescope like the JWST. The telescope will also help scientists discover exoplanets, which are very difficult to spot because of the way they interact with their host stars. Its powerful sensors will be able to observe these planets in more depth, including in some cases imaging their atmospheres. Understanding the atmospheres and formation conditions for planets could help scientists better predict if certain planets are habitable or not. Apart from studying the assembly of galaxies, scientists study galaxies to see how matter is organized on a gigantic scale. This, in turn, lets us see how the universe evolved. The spiral and elliptical galaxies we see today evolved from different shapes over billions of years. One of JWST's goals is to look back at the earliest galaxies to better understand that evolution. Scientists are also trying to figure out how we got the variety of galaxies that are visible today and the current ways galaxies form and assemble. However, most importantly, the James Webb Space Telescope will help us answer the most profound questions of all. Are we alone in the universe? And are we living inside a black hole? The JWST has already been on the hunt. And guess what? It found compounds called polycyclic aromatic hydrocarbons, PAHs, lurking around those gigantic supermassive black holes in 3 active galaxies. PAHs, these carbon-based molecules with ring-like structures, are like the goth kids of the universe. They're everywhere, from distant galaxies to comets in our solar system. Now, they're not just fascinating because they could be the building blocks of life, but also because they help astronomers track star formation. When ultraviolet radiation hits these PAHs, they go all flashy and emit infrared light, a sight that can be detected by the JWST's mid-infrared instrument, also known as MIRI. That's usually a sign that there are some hot, young stars hanging around. But wait for the plot twist. A brave astrophysicist, ISM Garcia Bernard from Oxford University, decided to take a peek at 3 active galaxies known as NGC 6552, NGC 7031, the spookily famous Stephan Quintet, and NGC 746. These galaxies are millions of light-years away in the depths of darkness. Now, what Garcia Bernard discovered will make your hair stand on end. In those central regions where the black holes reign supreme, MIRI found an abundance of PAHs. Sounds good, right? Well, here's where it gets chilling. The radiation near those supermassive black holes twisted the PAH's very essence. It transformed them into larger, electrically neutral versions of themselves. The smaller, electrically charged pHs vanished into oblivion, like being devoured by the darkness itself. But wait, there's a glimmer of hope. The larger pHs managed to survive because they found shelter within thin, dense gas-filled clouds. It's like they found their own protective hiding spots. So while supermassive black holes are supposed to gobble up everything around them, they leave some clues behind, like footprints in the cosmic sand. I know what you might be thinking. If black holes can do all of this, could it be possible that our universe is inside a black hole? Could the answer to the question that has plagued humanity for years finally be at our fingertips? With the James Webb Space Telescope, we may soon find out. The telescope will dive deep into the mysteries of our universe, and who knows what it will discover next. As we stand on the brink of a new era in astrophysics, the James Webb Space Telescope, JWST, is set to redefine our understanding of the cosmos. The JWST's advanced instruments, designed to observe in the infrared spectrum, offer unparalleled insights into the early universe, potentially shedding light on phenomena previously obscured by cosmic dust and distance. One of the most intriguing aspects of black holes is their role in galaxy formation and evolution. Current theories suggest that supermassive black holes, which are found at the centers of most large galaxies, play a crucial role in regulating star formation within their host galaxies. The energy and matter emitted by these black holes can influence the surrounding interstellar medium, either triggering or suppressing the birth of new stars. This feedback mechanism is essential for understanding the life cycle of galaxies and how they acquire their shapes and structures over billions of years. In addition to their role in galactic dynamics, black holes are also pivotal in the study of fundamental physics. The intense gravitational fields near black holes provide a natural laboratory for testing theories of gravity and spacetime. For example, observations of the behavior of matter and light near black holes can test predictions made by Einstein's theory of general relativity. Moreover, black holes are believed to be laboratories for studying quantum effects in extreme environments. Theoretical physicists have proposed that the interplay between quantum mechanics and gravity could be observed through phenomena like Hawking radiation, which predicts that black holes emit radiation due to quantum effects near their event horizons. The JWST's capabilities extend beyond black hole studies to include the investigation of the first galaxies formed after the Big Bang. By peering through the cosmic dust and observing the universe's earliest light, the JWST aims to identify the first galaxies and understand their formation processes. These early galaxies, formed when the universe was only a few 100 million years old, provide crucial information about the conditions and processes that led to the development of more mature structures observed today. In parallel, the JWST will explore the properties of exoplanets with unprecedented detail. By studying the atmospheres of these distant worlds, scientists hope to identify signs of habitability. The detection of atmospheric compositions, such as the presence of water vapor, carbon dioxide, or methane, can offer clues about the potential for life. Additionally, the JWST's ability to observe transits, when an exoplanet passes in front of its host star, allows for detailed analysis of the planet's atmosphere and surface conditions. One of the significant breakthroughs expected from JWST is its potential to resolve the mystery of dark matter and dark energy. Dark matter, an elusive substance that does not emit or absorb light, is thought to make up about 27% of the universe's mass energy content. Dark energy, which is believed to be responsible for the accelerated expansion of the universe, constitutes around 68%. While these components are not directly observable, their effects on visible matter, radiation, and the large-scale structure of the universe can be studied through indirect methods. The JWST's observations of the distribution and behavior of galaxies and galaxy clusters could provide critical data to understand these mysterious components. Furthermore, the JWST will play a crucial role in examining the cosmic microwave background, CMB, the afterglow of the Big Bang. By analyzing the CMB's subtle variations, scientists can gain insights into the universe's early moments and the fundamental processes that shaped its evolution. This analysis could help refine models of cosmic inflation, a theory that describes the rapid expansion of the universe in its earliest moments. Another promising area of research involves the study of cosmic reionization. This epoch, occurring roughly between 400 million and 1 billion years after the Big Bang, marks the period when the universe transitioned from being opaque to transparent. The JWST's ability to observe distant galaxies and their interactions will provide valuable information about the reionization process and the role of the first stars and black holes in shaping the universe. The JWST's observations are not limited to distant galaxies and cosmic phenomena. The telescope is also equipped to study objects within our own solar system, including asteroids, comets, and the outer planets. By analyzing these objects, scientists can gain insights into the early solar system's conditions and the processes that led to the formation of planets and other celestial bodies. In summary, the James Webb Space Telescope represents a significant leap forward in our quest to understand the universe. Its advanced capabilities offer a unique opportunity to explore the most fundamental questions about our cosmos, from the nature of black holes and dark matter to the origins of galaxies and the potential for life beyond Earth. As we await the discoveries that the JWST will unveil, one thing is clear: our understanding of the universe is about to undergo a profound transformation. The telescope's observations will not only address long-standing scientific questions, but also inspire new lines of inquiry, shaping the future of astrophysics for years to come.